Professor, you're muted.
I just realized that. Thank you. So, all right. So the recording started. Happy Friday. Half last day of lecture. Let's dive right in. Okay. So today is mostly a semester review, but we have a few other issues to take care of, and the first is the final self-assessment. Right. So we talked about this, I think, on Tuesday or perhaps last week, and that is this thing here. It is now an assignment, and you've already seen this, so hopefully you're prepared for it and can go ahead and get that done. It is right now technically due on Tuesday at noon. It'd be great if I had them on Saturday by end of day. If either of those dates are a problem for you, please, please, please just get in touch with me. Right. So, this is not meant to be a huge burden on anyone, but here's another way you can get to that link. So this is a separately graded form that is part of your final experience in this course. It's your chance to tell me what grade you should get and why. So, please, if these dates are a problem for you, please contact me for reasonable relief. All right. So, the final exam, hopefully everyone knows by now, is next Thursday. And I believe in the Eastern time zone, that's 11 till 1 in the regular classroom. And hopefully Ariana will be able to set up the feed as usual. I will be online, ready to answer any questions that comes up. Dr. Ozturk will be proctoring the exam, and he will be the one to, hand out and collect, and then he scans and sends them to me. So I have not heard from anyone that says they are have 3 finals on the same day, or have an athletic competition, or anything that's going to prevent them from attending the final as scheduled and in the classroom. So if there are any considerations, I'd ask for that to already be notified to me, but whatever comes up, please let me know as soon as possible. Because I teach remotely, it's rather difficult to make these arrangements. We certainly can if necessary, and it's accordance with the guidelines from the provost and the registrar on how these things go. But I just need just a little bit of extra time to cover those logistics. All right, so let's dive into kind of pulling this whole semester together, right? So we've gone through lots of different things as we've gone along, looked at lots of different topics, and now we've kind of gotten a taste of all those things. Now let's look back and put everything into context, right? So why do we communicate, right? If something is uncertain, if the probability of that event happening is 0, or it's meaning it can't happen, or 1 meaning that it's certain to happen, then there's really no need to communicate it. We already know it a priori, right? So we have this concept that Shannon called entropy, and it's represented in this one form by this equation. Sometimes we see a little shorthand where these are just probabilities. These are probabilities, and sometimes it's just written as like PR of X or something like that, right? But it's that level of uncertainty. Okay, and as we approach either 0 or 1, the entropy is smaller, right? But as we get closer or away from these things where maybe we're probability of a half. Well, that's like a coin flip, right? Heads or tails if the probability is a half. So we really don't have any information about it a priori, and so that's a lot of entropy that we need to send that, right? So how do we communicate? Well, we change some aspect of a signal, right? This course is all about signals, right? You learned about signals and systems last semester. Now we're using signals and all those tools you learned, not last semester, I mean last year, in signals and systems. So we changed some aspect of that signal according to the data. We send that signal across the channel. The receiver then examines the signal and estimates what were the original data sent, right? So we're mapping bits to symbols at the transmitter, and these symbols are suitable for the channel, right? We can't just send bits. Most channels aren't suitable to send just raw bits. Bits themselves are kind of a logical concept of a 0 or 1. So we'd have to map those to at least voltages or something, right? So to make them physically real. But typically in wireless communications, we're using some sort of nonlinear device typically to translate these baseband symbols to a frequency within a spectrum associated with that channel, right? So this might be in the megahertz, tens, hundreds, thousands, megahertz, 10,000, or megahertz, or 10 gigahertz, right? So and so on. So here's an analog continuous time, continuous valued signal here, and we can also write this as a sample time system, right? And we can vary a, omega, and or phi, right? The amplitude of the signal, the frequency, or the phase. It can be modulating this signal according to the data, and then that can be individually or in combination with these, right? And the data itself by this time might be coded, might have gone through some source code, source encoding compression, or might have some error control coding to it, right? So spectrum is a finite but very useful spectrum. That makes it valuable and also known as expensive, right? So we want to make the best use of it to support as many users communicating as much bandwidth or capacity in as little spectrum as possible, right? So we measure this with Shannon's capacity theorem. Let me go ahead and change that bandwidth here to capacity. Sometimes we're a little bit sloppy and we use bandwidth as this idea of how fast the signal is moving or changing, right? But more precisely, it's best to say capacity with as much capacity and as little spectrum as possible, right? So we measure this or assess this with Shannon's capacity theorem, and that's capacity is equal to bandwidth times log base 2 of 1 plus the signal power divided by the noise power, right? And this is then dimensioned in bits per second. Sometimes we talk about spectral efficiency. So we'll make this kind of a density type thing. We'll have the capacity divided by the bandwidth, right? So we're just taking this bandwidth and dividing both sides by it. And then our units end up being in bits per second per hertz, right? So if you're working in the cellular communications industry or something like that, this is the metric that you're tending to bandy about and brag about if your system is better than someone else's, right? So, all right, so how do we maximize the spectral efficiency? Well, we can start with, way at the beginning of this communication chain, right? We can compress our data using source coding. Oftentimes, we're wanting to do that in a lossless manner so that we can recover the original data exactly. We've just compressed it. Other times we might go with a lossy approach. We didn't talk about that. We didn't give any examples of that, but you're probably familiar with the JPEG image format. And as you compress it using that algorithm, the underlying algorithm, you end up with a lossy type system. You cannot take a highly compressed JPEG image and then extract back out the raw uh, uh, perfect high resolution image, right? So, but we did look at Huffman coding, and we noted that that thing is great. That's the one using the graph, and it is optimal, except that we need probabilities of the alphabet, right? So this is actually, I think I got these mixed up. This is a variable length code, and sometimes we'll use sorry. So if we don't have the probabilities, then we'll end up using lengthful ziv algorithm, right? And we looked at both of those. I think we did a MATLAB exercise on this, but we definitely reviewed the algorithm for this, and I might throw either one of these at you in a simplified version on the exam. So error correcting codes are essential to approaching the Shannon limit. So, we've compressed the source data to begin with, and now we're going to add some redundant bits. And this is really some overheads, right? So we've kind of reduced the number of bits, but now we're going to add the number of bits. It seems odd, but ultimately the trade-off works in our favor, right? So it results in fewer uncorrectable errors at limited signal noise ratios, right? So we might be constrained in our signal strength, and let's say on a deep space probe or something like that, like Voyager or Pioneer or whatever, and we're trying to get back that data, but we only have such a strong transmitter. And so we add these redundant bits in a structured way. And if we do it enough, we've got some correction ability, forward error correction. Right, so we looked at a couple examples, linear block codes. These are systematic in that the data itself shows up in the code word along with some parity bits, right? So these are decoded using syndromes. And conversely, we have convolutional codes. These codes have memory, right? Linear block codes don't have memory. And the convolutional codes have memory, and they are not systematic. In fact, we only send the parity bits in this case, right? So, and these are described via trellis, and we use that trellis along with the Viterbi algorithm typically, or should say often. That's one algorithm, and that can get complex in some cases, and so there's some other algorithms that we didn't really look at, although I mentioned that there are some efforts at turning machine learning at this to try to reduce the complexity of this. But we did go through an exercise and in lecture using the Viterbi, and you did both of these in MATLAB. So how do we maximize, again, continuing on? So we looked extensively at bandwidth efficient modulation schemes, right? So these are the constellations. We might be using an M-ARRY constellation or modulation technique where we have multiple bits, K bits being mapped into one of M symbols, right? And there's a log-base 2 relationship between these, right? So if you've got, if you're mapping K bits into one of M symbols, and you're going to need an overall a symbol set of 8 different symbols, right? So we take these 3 bits and we look at them, and then we choose one of the 8 symbols, right? And out of the constellation, we send that. Got dogs barking in the background. Sorry about that. Now, we can also leverage MIMO, and we looked at that just recently with a very high level, but here with multiple input, multiple output systems, we have several distinct channels. This requires some multipath interference in the channel to produce these different channels. And it's a considerable increase in hardware costs because each of these inputs and outputs, they're multiple, right? So we need multiple power amplifiers on the transmit side. We need multiple low noise amplifiers on the receive side. There's different ways of architecting this physically, but in general, it's going to require some additional hardware costs, but we do achieve a gain in the overall capacity. We just touched upon some of those capacity gains, and so I'm not going to pick on you to try to evaluate that. That's a little bit more of an advanced topic, but understand the concepts there, right? So how can we support many users in this valuable spectrum, right? So here we looked at some techniques to maximize the spectral efficiency, but now we want to support several or many users, right? And we can do frequency division multiplexing, where maybe each user gets a particular frequency channel to work in. So we divided up the overall spectrum into multiple different channels. We can use time division multiplexing, where we might send the symbols for user 1 at one instance, and then user 2, and then user 3, and then maybe we circle back to user 1 and then send user 2. And so each one is kind of communicating at separate times. So I'm hearing some background noise on the Zoom, so check your microphone if you have it accidentally open. So if you have a question, please just holler and let me know. So we've also talked about spatial multiplexing via cellular systems, right? Instead of just blasting out as much power as we can, we purposely shrink the cell size so that then we can put other cells adjacent, and they're actually operating oftentimes on other channels, but then eventually we repeat the same frequency if we get far enough away in cells, right? So oh, that's fun. Someone definitely needs to turn their microphone off on their phone. Then we also looked at code division multiple access. So this is kind of an extension of a spread spectrum technique, where we chop or chip the symbols using a special code. If we can give each user a orthogonal or somewhat orthogonal code between that, so that they don't interfere with other users don't interfere with them, then we can achieve some multiple access, right? And we can do the same thing with our other form of spread spectrum, which is frequency hopping. Yes, we also mentioned chirp as a spread spectrum technique, but we can hop to different frequencies, and if we if we can come up with some orthogonal frequency hopping sequences such that it's different users are always going to be on a different channel of frequency, then they won't interfere. Okay, so and then we kind of mash all these concepts together into this orthogonal frequency division multiplexing scheme, where we can allocate various subcarriers and symbols in terms of slots for different users. And we have this resource grid with the different subcarriers, maybe in the Y direction, and different symbols in a time dimension on the x-axis. And each of those little grid points, those slots, can be grouped together and assigned to different users. Okay, so all right, that all sounds good. Communication engineers tend to get paid lots of money. Why? Right? What makes this hard? Well, the big thing is channel impairments, right? So we're typically constrained in some manner by signal power. That might be by regulation. In this frequency band, we're only allowed to emit so much power energy, or our license may specify that, or it just might be that, well, we want to have a battery powered system that's pretty small, so we can't afford to have big power amplifiers with their big heat sinks and big power supplies and that type of thing, right? So somehow we're typically normally constrained in some manner by the signal power that we can transmit. And we're always confronted with this additive white Gaussian noise, at least in wireless communications. And so if we're constrained in the signal power and we're going to have additive white Gaussian noise, that's going to set our signal to noise ratio. As our wave propagates towards our receiver, it spreads out, and so the receiver only intercepts a tiny fraction of the wave that was actually transmitted, and so that SNR degrades the farther we go out, right? And we initially we ignored bandwidth limitations, but we do have bandwidth limitations, right? So we can't use the entire spectrum for our usage. We're always constrained to some extent there. And, antennas, power amplifiers, they all have finite bandwidths associated with them also, right? So then we have this multipath interference effect, right? Where our wave may take multiple different paths between the transmitter and the receiver. You might have a direct path, you might reflect off of other buildings or walls or floors or ceilings, or you might not even have a direct path, right? So that the different waves combined at the receiver antenna, their electromagnetic wave is inducing currents into that antenna, and then those sum up vectorially. So if there's kind of equal amplitude but opposite phase, they're going to cancel, right? So so that's going to be on a frequency dependent thing, because phase is over distance is frequency dependent. So you might have notches in the channel, right? Where your signal power, your received signal power almost vanishes. Right? So then we talked about nonlinear effects, intermodulation distortion, typically dominated by the power amplifier, but other components can have some nonlinear effects also, and these generate spurious frequencies that can end up interfering with us, right? So we can have some interference from non-cooperating spectrum users. That might be just kind of a fact of life if we're operating in a shared unlicensed band, like where our Wi-Fi and Bluetooth and Zigbee type devices operate in, then we're required to be able to accept any interference any other radios produce to us, right? So we've got to design our system so that we're tolerant to interference. Or we might be in a situation where an adversary is purposely trying to jam us to try to gain an advantage over us. So interference makes it hard. Most of these impairments are random processes, and even the data sources are often stochastic in nature, right? So random, and the just a note that the channel does include all the effects of the power amplifiers, filters, low noise amplifiers, mixers, the local oscillators that are part of that frequency translation mixing process, right? So, how do we deal with all these challenges, these channel impairments? Well, first of all, we got to wrestle with probability theory, right? Because these things are random processes, right? So fortunately, we can normally oftentimes assume stationarity, where we're really only concerned about time offsets, and we're not concerned about the absolute time. We don't need to know that this transmission started on May 4th at 11:56 a.m. Central Daylight Time, right? So then we're just concerned about how the time spacing and deltas and that type of thing. Then we can also oftentimes claim ergodicity, or that our process is ergodic. And this is basically that the system has the same basic statistics, whether you're sampling many different processes or one is sampled across time. Right. So this one's easier to deal with in life, right? So we can take a single instance of a communication process and just sample it in time. And I'm hand waving here. There's a more formal definition to this, but it's the idea that we can really just look at one signal and sample it across time and end up having the statistics we need to do the rest of our analysis. So many random variables have a Gaussian distribution. Okay, if they don't individually, then oftentimes the central limit theorem applies, and so that really helps us out. So in communication systems where we're working with the Gaussian distribution all the time, occasionally we deal with functions of variables that have Gaussian distributions, and we end up with maybe a random variable x times a random variable y, and we end up with a little bit more complex type of distribution. But the Q function is tightly related to the Gaussian, and we've done some work with that and some MATLAB exercises, and this helps us look at the sum of a tail of that Gaussian distribution, right? And so we use this in our bit error analysis type of activities. We looked at autocorrelation and cross-correlation. And autocorrelation is when you're taking the same signal and you're kind of sliding against itself, and where it's lined up with zero offset. Sometimes we call those lags, so zero lag. Then we should have a peak, right? Because we're autocorrelating that. Now, as we start to slide off and we have some time separation or some lag separation, then typically we want that then that autocorrelation, that kind of multiplying and summing of all those overlapped values to be very small, right? So when things are lined up, we've got a big peak, and it's narrow because as we slide off, our value drops down a lot, right? So when we look at things like CDMA codes and synchronization codes and that type of thing, we're looking at their autocorrelation and their cross-correlation properties. Cross-correlation is the same thing, so a similar thing, except we're dealing with two different signals, right? And we're looking at their similarities between these. And if you're familiar with convolution, which you should be, then it's kind of an easy step to get here. There are some differences. We don't do the flipping but they're very closely related. Then we also noted that the power spectral density is related to the Fourier transform of the autocorrelation, right? So the PSD of a signal is essentially its frequency response. If we're dealing with a deterministic signal, we simply do the Fourier transform on a time domain, right? But when we're dealing with random variables or random processes, then we end up doing an autocorrelation and a Fourier transform. So we didn't really do any exercises with that, but that's kind of foundational. So we it's one of those things that we tend to take for granted, but that's the formality of it, right? So again, how do we deal with these? We characterize our constellations with the minimum Hamming distance, right? So we found that at the receiver, the signal's been corrupted by noise and maybe some other distortions, impairments, and we want to, all the receiver sees is a received signal, right? And it's going to map that received signal, however impaired it is, to the nearest constellation point, right? And we kind of developed some math for that. But if the noise or impairments has been so bad that it pushes that received symbol too close or across that decision boundary into another decision area where it's now closer to a different constellation point, then we're going, the receiver still doesn't know any better, right? And it's still going to map it to the closest constellation point. In this case, it's going to be wrong, right? So if this distance between the constellation points is greater, then that's error is less likely to happen, right? We need more noise power or less signal power. We need lower signal noise ratio in order for that error to happen. But we can't just arbitrarily increase that Hamming distance between constellation points, because ultimately our power or energy that we need to send this is going to be driven by the outside constellation points, right? And the vector from the center out to those constellation points, that's going to be its amplitude, and square that, you get the power. And now so we're constrained by that. Now technically we want to average all the constellation points, but as you grow that constellation to try to increase the Hamming distance, then we've got energy problems. If we just keep adding constellation points, and we're, say, going from a Comm with 4 constellation points to a 16 Comm or 128 Comm or 256 or 1024, then if we're constrained by the total amount of peak power that we're transmitting, then all those points get squeezed closer and closer together, right? So so we design constellations to maximize the distance, but consider the difficulty and amplification and equalization, right? So by the time we receiving that constellation, it will have gone through a whole bunch of phase as that wave travels from transmitter to receiver, and that has the effect of rotating, just like a phasor. Remember your circuits, probably circuits 2, second semester, where you studied phasors, right? So that whole thing's going to be rotating around and around for every wavelength that it propagates out to us, right? So we've got to derotate it or equalize it. We've got to work out, get rid of these channel impairments. And we did a little bit of a MATLAB exercise where you're mostly we're just running some examples and observing the results, right? So we calculate our bit error rate by considering the tails of the Gaussian distribution, right? And as you know, where we assume that our only impairment is Gaussian noise, and that Gaussian distribution that crosses into a different decision region, right? And so we're to get that probability, we look at the area under that tail, right, from that decision region out to infinity, which maps neatly into that Q function that we talked about earlier, right? So I think we did that on either the first exam or the midterm exam, where you did a little bit of an assignment on that. So question on that. So then we also have this symbol interference. This limits our maximum rate in band limited and or nonlinear channels, right? So we can reduce intersymbol interference just by limiting our maximum symbol rate, but you know, that's not good. We want to talk fast, right? So we can use raised cosine filters. These exhibit nulls at the other symbols' peaks, and even right around those nulls, we kind of have a flatter region of these time side lobes than if we just used a simple sinc x or sin x over x type function, right? So we saw that these raised cosine filters are parameterized, and kind of one extreme they'd be a sinc function, at the other extreme they'd be just a rect function, but they're used to kind of trade off that performance there. So there's some other techniques that we didn't look at. Of course, that can be said for almost everything we do in this class. There's always other ways of tackling these things, right? So all right, so now we've done all this work at the receiver. How do we actually estimate what was sent, right? So we talked about this maximum a posteriori. Well, I hope I spelled that right. I just did that from memory. I never took Latin. Chooses this map type receiver, chooses the symbol that would most likely produce the effects at the receiver, right? So it's you know, uses Bayes' law, Bayes' theorem to kind of flip that conditional probability around, right? So you should kind of understand that fundamentals there. And then we noted that, well, there's a little bit simpler receiver, a maximum likelihood receiver, and this is optimal when the symbols are equal probable, right? But if they're not equal probable, then you need to go with this map type receiver, right? And so these are kind of describing the receiver in mathematical terms or probabilistic terms, and we're using our probability math to describe these things, right? And then when we actually implement it, then we can take that math and we can you know, develop physical receivers around that. And we did that with a correlation receiver, right? Where each kind of stage of that receiver is implementing the integrals and whatnot that are part of this map process. And then we also introduced this match filter receiver, which is a different thing. It's convolving the symbol shape, right? So we take this filter and we design it so it matches the symbol shape, and so when they're convolved, we should get a nice little peak, right? And we notice that we between these two different styles of receiver, we get the same results at the sampling instant, right? They are going to be very different, potentially very different in between times, right? But we're really only concerned with the results at the sampling instance, right? And little n times capital T, right? We've got this periodic sampler cruising along there. So, all right. So we've done some good engineering work, right? But as engineers, or at least our managers, always want to measure and decide how good a job is he or she doing, right? Or, you know, how are we going to evaluate this system that we're building up, right? So there's some different metrics that we have in the system, right? We've already talked about signal noise ratio. Sometimes we kind of cast that in terms of this EBNO, the energy per bit noise, and that noise there is a power spectral density. And then we will go through and kind of evaluate our bit error rates versus SNR or EBNO. We might do a symbol error rate versus SNR and a bit error rate versus EBNO, where we notice that at the symbol level, that symbol can kind of encompass a number of bits, right? So when we're kind of going from a symbol error rate to a bit error rate, or the signal power to the energy in the bit, we're kind of mapping, taking that symbol and then allocating certain energies or certain error probabilities to individual bits, right? So then we have this concept of power spectral density. So yes, we're concerned about bit error rates. We're often concerned about our spectral, how much our energy is in the channel versus maybe some of our energy leaks out. We didn't really talk about that a whole lot, but it is an important aspect. You're going to be far more concerned about measuring power spectral density when you get into more of an implementation type of thing, and that'd be more of a circuits and systems type of course, right? So we looked at cascaded noise figure analysis, and we also looked at cascading. We looked at intermodulation, distortion, and third order intercept points. This describes our nonlinearities in our system, and we also looked at how these cascade also, right? So we noted that it's usually the first thing in your receiver chain that dominates the overall performance of the system in terms of noise or in terms of intermodulation distortion. So then we also have, like when we're looking at channels, and in particular multipath channels, then we've got this fast fading where we might have these deep notches in frequency, and that's kind of a concept. It's kind of squishy. So when we want to really get specific about measuring it, we can either talk about coherence bandwidth or the delay spread. And these are related to each other kind of through a reciprocal relationship, right? So this is frequency and that's time. All right, so we did a lot of simulating of systems, right? So some of the things that hopefully you've kind of absorbed as we've gone through this is, for bit error rate, we need to make sure that we have enough data points to make sure we see enough errors to get a good calculation, right? So if we expect to see a bit error rate of 10 to the minus fifth, and we only do the analysis with 1,000 data points, well, most likely we're going to get 0, right? So 0 divided by 1,000 is 0, but how good of a number is that, right? So really, if we're expecting to see a bit error rate of 10 to the minus fifth, well, we're going to need like 10 to the fifth samples or bits to begin with to even just get one error, right? So on average, if you had bit error rate of 10 to the minus fifth and you had 10 to the fifth data points, well, on average, you're going to see one error, but sometimes you might see 0, sometimes you might see 2 or something like that. So you're going to need 10 or more realistically, at least 100 times that, right? And now when you run your results, well, let's say you get 100 bit errors, you divide that by 100 times 10 to the fifth, and you should get a bit error rate of 10 to the minus fifth, right? So then anytime we're modeling a system, simulating a system, whether it's communications or any other type of system, we really need to kind of decide what we want to study in detail and what we can kind of simplify, right? Because if we try to model everything precisely and accurately and all, it's going to get so complex that we might as well just build a system, right? We simulate a system so we can get an idea of what its performance is going to be and how it's going to actually operate before going to all the expense of building it up, right? So we've got to kind of trade off the fidelity and resolution of the simulation with the time and budget that we have to actually do the simulation. And so, it's helpful to understand really what we're trying to study first, right? And, you saw in using MATLAB is fundamentally a matrix algebra solver programming system. And so we try to put our data, our systems, our effects, our modulations, everything we try to do in this matrix algebra so it fits neatly into MATLAB, and that way we can speed up computations and also kind of keep our code clean. So we don't have tons of for loops in there, nested for loops, 3 or 4 levels deep and that type of thing. We saw that most of the time we didn't actually have any delays in our communication system. We kind of assumed that our channel would have some effects in terms of noise and that type of thing, but we didn't actually program in a delay except when we started working with those raised cosine filters, right? And they had some finite delay to them. In real life, yeah, a channel has delay, and it might have some Doppler, and that delay might change, right? So we need to we need to understand if we have a delay, and then how we're going to align the received data with transmitted data, so we can compare them bit by bit and sum up the number of errors, right? So if you just reflect back on some of the things you did, you've already kind of tackled that there, right? So then we just recently did something on machine learning. So just toss this in here, right? So we can dynamically access spectrum on an opportunistic basis. We can simplify decoding without the overhead of channel state information. And so this is involving some equalization and that type of thing, right? So so that just is, again, kind of helping our process. So we sometimes find that there's a truly optimal way of solving that, but that optimal way of solving a problem is very numerically intensive, or we need to gather lots of information, and that takes time and therefore adds delay to a system, right? So machine learning can often help us around some of those things and find lower computational ways. Machine learning, or neural networks are a good nonlinear function estimator, right? So because they've got nonlinearities inside them, and they've got lots of degrees of freedom, all those different weights and biases that we can adjust, then we can do a really good job of implementing these nonlinear functions, things that don't look like a straight line. All right. So what kinds of machine learning are relevant in communication systems? Well, we looked at supervised learning, where we train with a large set of labeled data, right? So we collected a very large set of data, which is kind of like we have the questions and we have the answers, right? And then we do that supervised learning. We mentioned unsupervised learning, but we didn't really explore it, right? But that's where you might look for clusters or trends in data and that type of thing. But we did talk about reinforcement learning, and that sometimes described as a trial and error process, where we explore to find the best solution, right? So think about the mouse in the maze trying to find his cheese, right? And so he's going to explore, and maybe eventually with enough trials, he'll learn how to get to the end in the quickest way, right? Then we looked at neural nets as one way, a very popular way of implementing these learning mechanisms here, learning procedures. And they are composed of layers of interconnected neurons with weighted inputs and biases and a nonlinear activation function for each of these neurons, right? And we tend to organize in layers with some number of neurons, and then we have subsequent layers, and that structure is easier to work with and just kind of some randomness, right? But some I should say some neural networks, some very important ones, have these skip connections where let's say layer 1 might not just connect with layer 2, but it might jump across and connect with layer 3 also, right? But these neural networks are trained via back propagation. And so we take these answers, the labeled data, and we compare it to what the network is currently in its current state of learning producing, right? So we present it with the questions, the data, and it forward propagates and estimates some answers. We compare those with what we know are the true answers, the labeled data, and we look at those differences, right? And then we back propagate using something like a gradient descent, where we're taking derivatives and we're trying to iteratively reduce the difference between what we're currently predicting and what we know the answers are supposed to be, right? So then we noted that, well, kind of the basic neural network is does not have a state associated with it, doesn't have any memory. You put an input and you get an output right away, right? We got to spend some time, some CPU or GPU cycles calculating it, but we get that output right away. And we change your input, and the output changes to just reflect what the new input is, right? And it forgets what it did in the past. Well, with signals, we want to have some memory in our system, right? So we tend to use recurrent neural networks when dealing with signals, because these networks have memory, right? So, and they can relate to different portions of the time signal together. So now, how do we approach a new design, right? So you've taken this course, perhaps you're graduating, maybe you got an offer from someone, and you're going to be a new communication engineer, and you're going to be somewhat responsible for developing a new system, right? So actually, in the New York area, the New Jersey area, have a long history in communications. Bell Labs is here, and Claude Shannon did some of his work here, and so some of the names that you would see in some of these things, they all worked in and around the New York, New Jersey metro area. A lot of the original telecom, and still to this day, Qualcomm's got some offices here, even though they're based in San Diego. Over in Long Island, there was kind of a whole ecosystem around microwaves, and more of the implementation of microwave systems and stuff. So there's a lot of heritage here. So let's say you get a job, right? So how do we approach a new design? Well, first of all, we need to kind of define our objectives, right? Also known as use cases, right? So we looked at the 5G use cases just the other day, and what is the market looking for, right? What's that market pain? Hopefully you've looked at this kind of market driven and design process in your capstone course, right? So Consider constraints. Okay, again, in Capstone, hopefully you learn that most designs are constraint driven, right? So you got to identify your constraints. Maybe you've got regulations. There's a little bit of kind of overlap between constraints and what the market's looking for. The market may be looking for a battery powered, small portable device. That becomes a constraint for you if you've identified that that's what the market wants, right? And now you've got energy constraint on your system, right? So at this point, now you should probably consider what standards exist, right? We don't normally get paid as engineers to reinvent the wheel, right? It's been done. We might improve on it, but we're first going to see what standards exist, right? So that might be the 5G or 6G managed by the 3GPP organization, or it might be a Wi-Fi, which kind of at the lower levels is standardized by the IEEE, and higher levels is more alliance, Wi-Fi alliance, and Bluetooth and Zigbee. Some of these are formal standards, some are de facto standards, but we want to see what standards exist and lean on them, right? Then and these aren't in strict time order, right? But kind of quasi ordered, right? So now at some point we want to really characterize our expected channel, right? And we looked at different ways of maybe doing that analytically, but also noted that on a practical basis, channels they're complex, right? And they are definitely random, and particularly in mobile communications. And so different people, different organizations have done these measurement campaigns or characterization campaigns. And so then we can say that an office environment has certain characteristics in the, let's say, microwave, low microwave region, or VHF or UHF region, and urban environments, suburban or rural type environments will have different kind of empirically developed characterizations, right? But we need to understand all those different impairments and how sophisticated of a system do we need to come up with to deal with those impairments. If we've got a pretty clean channel, maybe we don't need to have that sophisticated of a system, right? So part of that is that are we mobile, right? Is our channel time varying, and to what degree, right? And maybe we didn't really talk a whole lot about Doppler, mentioned a few times, but maybe we've got some Doppler effects involved. You might have that in a low Earth orbit LEO type constellation, like OneWeb or Project Kuiper from Amazon, and Starlink is the one that was escaping my memory right there for a minute. So there you have a big Doppler effect because satellites move really quick, and that satellite's going to kind of come above the horizon from your perspective on Earth and set on the other horizon in about 10, 15, 20 minutes at the most, right? So that thing is really cruising. So you're gonna have a big Doppler shift at the beginning and then at the end, right? So so how many numbers of simultaneous users are we going to try to support in this these use cases? Is just a few? Maybe we can get away with a simple frequency division or time division multiplex system. But if we're looking at lots of users in a fairly complex channel, then we're probably being pushed into more of an OFDM, A type of system, orthogonal frequency division, multiple access, right? So it's just a little bit of a tweak on OFDM itself. So ultimately, then we look at what is the least complex solution, right? Because one of our constraints always is cost, right? So we don't want to price that system more than we need to. Then typically, almost all the time, we're going to do some simulation before building that system, right? So you can imagine if you're building a Starlink constellation, you're not just going to start throwing things together because you had a good idea and spend the millions of dollars to build the hardware and launch the hardware and operate the hardware. And boy, I hope that works. You're going to do a lot of simulations before building that. And, again, that simulations might be very high fidelity at the physical layer, but then at maybe the higher levels, we make a bunch of simplifying assumptions, or vice versa. Maybe we assume that physical layer is just, has a estimated bit error rate, and we don't simulate it directly, right? We just throw in an error every 10 to the fifth bits, and we focus our simulation on kind of some higher layers of the system, right? So we got to figure out what we need to simulate. So and then when we are simulating, what simplifications are we assuming to make that simulation practical, right? So we need to always keep that in mind. And we talked a lot about how in your early days when you first learning electrical engineering, you assumed everything was linear, everything was time invariant. The whole effect of a resistor occurs at a specific node, right? So you could do nodal analysis, and it's not really distributed throughout a physical region. None of these assumptions apply in the real world, right? So we need to understand, though, the implications of any of those assumptions, because trying to simulate these things more fundamentally from first principles gets very expensive very quickly, right? And all of this needs to be done to be able to handle random effects, right? So we're going to have some random number generators in there. We're going to repeat these things many times, right? So when you turn in your assignments, you're turning in one iteration of it. But when I run your code, I probably get a little bit different answers than you did on the topics that had some random number generators in them, right? And so in reality, you're doing that over and over again, and then doing your means and your variance or standard deviation calculations and that type of thing, right? So always we need to look at our results, right? So one of the things that I've noticed over and over again is that some of y'all would turn in an assignment, and it just the numbers you get just don't make sense, right? If you get a bit error rate of greater than 1, that can happen, right? That means you're getting more bit errors than you actually have bits, right? So and in fact, if you get a bit error rate of 0.5, that is essentially as good as flipping a coin. You don't need to go through all the engineering and expense to build a communication system. Just tell the receiver to just flip a coin, and because you're going to get a bit error rate of 1/2 then, right? So you should be able to look at your simulation and see, does that bit error rate make sense, right? Did you calculate it using a Q function, and then and you got something like 0.0077? This is one of our assignments, and but then when you actually ran it, you end up with like 0.1, right? When you created 10,000 samples and actually simulated and counted up the number of bit errors, right? So they should match, right? They should come close to each other. Not gonna be exact, but they should come close to each other, right? So always, ultimately we verify our simulations by building the system, right? But we do the simulation before we build the system, because we want to avoid that expense, or we want to stress the system in a way that maybe isn't practical, right? And so we need to, if you're this is a different topic of simulation, but you're building a flight simulator and you want to see how your pilots react during a crash. Well, you want to do that in simulator, not in real life, right? So understand what simulation gives us, what its limitations are. All right, so that's the end of that. And again, we have this preview up there, and I think I've posted this already. I've maybe added some little items, and I will refresh these, and I will put up a last year's final exam. Probably won't give you the answers. I don't know. That might be too easy. Although I don't know. If someone thinks I should, I could. But these are the type of problems that you should be able to do. And again, there's some caveat to this, and that last year, instead of doing MATLAB assignments, the students did more kind of traditional homework assignments and stuff. So some of these things that they would have been doing by hand, you've done in MATLAB. And I hope that was a good experience, particularly if you end up as a practicing engineer, you're going to use MATLAB. It's going to be, or Octave or some equivalent to it. Your skills are going to be built around that. But you do need to understand the theory that's in all of those things, right? So, but yeah, so there's some error control coding. Here's, I give you a syndrome table. I give you an HT and a receive vector, and then you're going to multiply this times this, and that's going to produce some syndromes. You're going to look up the syndrome. It'll give you one of these, right? If it's 0, there's no errors. If you get one of these others, this is your error vector, and then you XOR this with your receive vector on a bit by bit basis, and then that gives you the corrected receive vector, right? So, or I could, ask you to use the Lempel-Ziv algorithm, give you a short one here, and you break it up into phases, and then, create your, these addresses are going to be incremental, and then you create your code word by that process, right? So, so I could refer to a trellis, and this is calculating the path metrics, right? So this is a little subset of a Viterbi algorithm, right? So look at this trellis here and kind of fill in these blanks here, right? So be able to run that through. What channel matrix best reflects the Alamuti MIMO technique? Okay, so we covered that very briefly, maybe not as in depth as I did last year. So, but yeah, you should understand that some of the concepts about MIMO there. So yeah, so yeah, maybe some of these are things we didn't exactly cover, but well, like describe the 3 use cases of 5G we discussed in class, right? So what distinguishes cellular communication? So these are testing your concepts, name 2 standards organizations. God, I'm sorry, I've not been sharing that with you. Sorry, I was going through all that on my other screen. Okay, so but yeah, so communication symbol maps 4 bits to a set of symbols. I'm telling you here that K is 4, right? You should be able to figure that out from the words. But how many different symbols are required, assuming memoryless modulation? Well, that's 2 to the 4, right? Would be 16 different symbols, right? and then how to relate symbols per second to megabits per second. And then how do things change if we increase the number of bits to 6 from 4, while keeping the peak power signal the same. Basically, we're constraining the outside of that constellation. And will the error rate increase or decrease, right? So assuming an AWGN channel, we'll think about what happens if we're constraining the outside of it. That means that those little constellation points are getting closer together. Their Hamming distance is shrinking, right? What kind of impact is that going to have on there? Here's, we looked at some binary signaling. We looked at antipodal, we looked at quadrature, and we looked at on-off type keying, right? So be able to sketch constellations, show the decision boundaries, and you should be able to use this type of equation here, where if you know the distance, the minimum distance, you can plug and chug here and look up in the Q table that'll give you and end up with your probability of a bit error, right? So sometimes we can get that D12 here from the energy and the probabilities involved there. So, or in some simple cases, you can just kind of like plug it right in. So, what time is it? Okay, I got 3 minutes here. What advantage does a symbol shape as a raised cosine have, or a sinc x shape? We just discussed that earlier. Here's determine a code word to send given the input bits and the generator matrix. So you're going to multiply this by G, right? And so that should give you a code word, right? So here we have 4 by, this one's 4 here, and then this is our length of our code word, right? So your code word should be as long as the number of symbols and or columns in this generator matrix, right? So here's the one I was describing when I wasn't. I just described this by voice, and but yeah, you're going to take the receive vector and multiply it by your parity check matrix. That's going to give you a syndrome that gives you your error vector, and then bitwise XOR that with your receive vector to get the uncorrected one, and then recognize that, okay, in this one, you got to figure out what the systematic part of it is, right? So in a generator matrix, the systematic part here is the unity matrix, right? And then this H is the kind of rearrangement of this generator matrix, right? So we've got this unity down here, right? Whereas this is the other part of it. So in that MATLAB, just by convention, put the parity check bits at the beginning versus the end. So don't assume that it's one, it's either at the beginning or at the end. All right, so I think that's it. I will very shortly, like within minutes, be sending out an email to those that do not have all of their homework assignments in. I think most of y'all, try to get that in, but I think in a few cases you may have not realized that you missed an assignment. You forgot about that. So I will send that out to you. I will grade those on a best effort basis. But yeah, you need to get those in right away. They are beyond late at this point, right? So, but I will, as a courtesy, let you know where you stand there. So your task are to complete any homework assignments, complete the self-assessment, study for your final, and do your course evaluations. I think this morning my rate was 8 students had done the course evaluations out of 25. So please do that. I think there's some deadline, and I know you got lots of finals to study for, but try to squeeze that in. But you must complete the self-assessment. That is part of your grade. right? So that is not optional. All right. Thanks, and we'll see you on Thursday.